To be fair, Marlboro, they got voted out of Quebec City.
All right, so today we are looking at predicting products double replacement, which I think, did you watch the videos on that? Yes? So if I was to take some lead 2 nitrate, oh, this was labeled back in the good old days. We used to have a lab aide who didn't actually know chemistry. Pardon me? No. We have a student who's helping out, but no, we used to actually have like somebody whose job it was, they got paid by the district to be our lab person. So this is lead 2 nitrate.
That's exactly what I was looking
And in fact, I should be doing it on here, shouldn't I?
So
Yes.
I talked to Mr. Ryan.
Yes.
The senior race starts at like 4 o'clock.
Okay.
So I think I might stay until like 2.
Whatever makes you happy, I'm happy.
The more I'm in class for.
I understand. Yes. Write down the formula for that. Anywhere. Pick a piece of paper. There's 3 blank paper back there for me. Go grab some free blank paper and write down the formula.
Whoa. That's how matter works.
Okay, so we have lead 2 nitrate. You're going to write the formula for that. And you're also going to remind me what you know about compounds that contain nitrate. So nitrate-containing compounds are what? All soluble. Okay, and we are going to put this together with potassium iodide. So you're going to write the formula for that one as well. And once you got those two written, I would like you to predict the products of that reaction. Are they all aqueous? What do you think? They're both soluble because why do we know that potassium iodide must be soluble? Because it's got an alkali, and alkali compounds are all soluble. Okay, so you're going to write your reactants and you're going to predict your products, yes? There's water here, but it does not take part in the reaction. And I'm just going to go grab one more thing so we can do something a little bit fun with this. Did we get that for lead nitrate? Yes? Okay, good. Did we get Ki for potassium iodide? Yes. What state did we put on each of those? Aqueous, excellent. Now, when you're predicting the products, first of all, what kind of reaction is this and how do you know? How do you know that it's a double replacement? We have an ionic compound and an ionic compound, and therefore it's going to be double replacement. Yep. How do you predict the products of a double replacement reaction? Yes. You switch around the metals or the non-metals. One way to do it is to take your outside ions and combine them, and to take your inside ions and combine them. And I like to do it like that because then I always remember that my cation has to go first in the formula. So my question to you is, should my products look like this? What is wrong with what I have done? They're not balanced. Why are they not balanced? PB has a 2 charge, yes, because nitrate is -1 each, and there's 2 of them. So PB has 2 plus, and I has 1 minus, and so it can't be PBI, it must be PBI 2. Yes? Why can't they what, sorry? Oh, switch their charge. That would involve having to gain electrons or lose electrons from somewhere else. There's nothing here that wants to, say, take 2 electrons from the lead. Okay, so yeah. So it's going to maintain its charge. We will get into what we call redox reactions later, and that's where the electrons actually do move from one species to another. Okay? And how about my potassium and nitrate? How do those go together? Yeah, we just have a +1 and a -1. Yes. You could put potassium nitrate first and lead iodide second. It does not matter. As long as they're on the product side, it does not matter which one comes first. So you could write same deal. And you could do the same thing for the reactants. They could be in either order. It doesn't matter. Did you have a question? That was your question? Yeah. So reactants can go in either order. Products can go in either order, just as long as the compounds are actually the correct compounds. We're good. Okay? Now, can you please tell me the state of the KNO3? How do you know that it is aqueous? It's got a nitrate and it's got an alkali. Okay. Now let's say that I told you that this reaction forms a precipitate. What is a precipitate? It is the solid that forms in a double replacement reaction. It means some other things too, but in this context, that's what it means. Yes? Because it falls out. So rain falls from the sky, and the precipitate falls out of solution. Shall we watch it fall out? It's falling. Okay, so shall we watch the precipitate fall out of solution? What? It's like the video. Are we ready? 5, 4, 3, 2. Whoa. Now, how do I know that there is a solid in there? Yes. It's not clear anymore, okay? When light hits a solution, the ions are so tiny that the light just goes right through them, goes right past them. There's tiny little solid particles in here, though, that are big enough that the light will bounce off of them, and that's what makes it cloudy, okay? Now, we could sit and wait for this to fall all the way down. They're tiny particles, so it will take a while. Or we could use this little thing right here. Has anyone used one of these before? This is a centrifuge. It is a spinny thing. So if you would like to come and look closer at it, please feel free. I'll abandon the back of my desk.
Yo, it looks like that thing that I saw in that
Spin
thing.
stuff.
Yeah, crazy.
I did.
Why does it look like a bubble machine
Russian
major?
roulette.
You can spin it.
Yo,
It spins.
if it lands in one,
You see?
imagine.
How do I leave?
Yes. Thank you, Nate. Ah. Ah. Why do I keep looking at it?
You guys, hey Arvin. Do you think this works better or our hands or my hands? Hey, this Charlie, this is what my hands do. Ronaldo.
I think I'm just blind.
Wait, so you're telling me your hands go like this, bro? When you're doing it, you go like this.
Doing what?
You're shaking it, bro.
Right on the computer.
Son,
Write something.
you write something. Child. Daniel, what were you doing in topside? Wait, nothing.
Once you're done, you can go sit back down again because like it's not really that exciting to watch. Okay? Huh? I don't know.
Do you stick it in like that?
Want to? Are we allowed to watch if we want to?
Yeah, you can watch if you want to, but you need to come back here so you're not blocking.
Not blocking like I come.
You're very talented. Now, you guys are gonna move around here so those people can see. Okay, they wanna watch, so we're good. Now, you are gonna get a chance to use this later this year, okay? And we're going to just turn this on right now. They're gonna not be able to do it because they haven't been listening, okay? And what time did I turn it on to? Oh, hang on, we have a problem.
Why are you vibrating?
Ah, I know exactly why it's vibrating. I did not balance it, silly me. I should know better. Okay, so, do you see how this test tube is empty? And this test tube is full? Don't do that. Okay, do any of you still have the old style laundry basket, or not laundry basket, laundry machine that top loading laundry? Anybody? No. Is it just me? Yeah.
It's a laundry machine.
Well, I don't have it,
But you know it, you've seen it. Okay. So if you have that, it goes into spin cycle and it spins around. And like if you have an unbalanced load, your washing machine will literally go and it starts walking across the room. Similar problem here, right? Because I hadn't balanced it. I was like all distracted and whatnot. And anyway, so now it's balanced. Now it shouldn't judder around and things like that. So I'm going to close it. I'm going to turn it on. How much did I turn it on to? 10. The reason I turned it on to 10 is not because I want it, doesn't matter. I don't want it to go for 13 minutes, but it doesn't work if you turn it on to like 1 minute. It just doesn't, it thinks you're wanting to slow down at that point. Okay? So just turn it on to whatever, and then when you're done, like, so we just wait for a little minute here. We could sing the Jeopardy song.
Are those the numbers or time, not speed?
Time, not speed. Da 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 da. Da 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 da. Pay attention. Da 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 da. You guys missed the ding. They're so noisy. They missed the ding. That ticked me off. Very disappointing. You guys were so noisy, you missed it when it went ding. And the ding is like half of the experience. I'm gonna do it again, you're gonna listen for the ding. Yeah. Okay. All right. So now hopefully it's been for long enough. You're not supposed to do this, but I kind of always do. Okay. This obviously is the one that didn't have anything in it. And now, can you see how it's all ended up on the side and at the bottom? Okay, so we've actually managed to separate the liquid from the solid. And if I pour this one out now, do you guys know what it's called when you pour off a liquid and leave the solid behind? It's called decanting.
Is that why it's called a decanter with the wine?
That's why it's called a decanter with the wine. Because it used to be, when they made wine, there would actually be some of the yeast and stuff left in the bottle. And so you didn't want it there. So you would decant the wine into the decanter so that you would leave all those dregs behind.
That's a swirly.
This thing?
The
The
decanter.
decanter, it's a jug that you put your wine in. Okay, now, here we go.
Sangria picture.
Here we go.
Why's the liquid so
Oh, this is a solid.
Yes. So we have separated out the solid. What do we call the solid? The solid is called the precipitate. This, the liquid that is left behind, is called the supernatant. Supernatant. Okay. And what's in here still? Potassium nitrate is in here, and our lead iodide is here. Okay, you guys can go sit down again.
Why does no one want to stay until 7?
So our lead iodide was the solid. That is the precipitate. You can abbreviate precipitate as PPT. Okay, because precipitate is really long. Have we balanced this reaction yet? No, we have not. So we could balance it by putting a 2 where? In front of everything here? No, okay. In front of most things though. Let me just find my erase button. There we go. Okay. Oh, that did not work. There we go. Okay. But if we put a 2 here and a 2 here, we're good. All right. And we're just going to draw a quick little picture of what that looked like after we spun it in the centrifuge. So we spin it in the centrifuge. If we left it long enough, it would settle out on its own, okay? So we spin it in the centrifuge and the solid goes to the side and the bottom. So the PBI2 precipitate goes to the side and bottom of the test tube. So then our picture would look like this. I'm going to draw an idealized picture where it's not all over the sides. Okay. There's our test tube. Here's our PBI2. You can make whatever color you want. I just happen to actually have yellow. So I was like, why not? Why not do it? So this is our PBI2 solid. And then up top, we still have the liquid, and that is the KNO3 aqueous. So this is the precipitate. This is the super. Super means above. Natant. And I'm not quite sure why natant, because natal has to do with like birth, so it's above the birth. I don't know. It's above the birth of the precipitate. I don't know. Yes. Is potassium nitrate poisonous? I feel like, no, I don't think so in particular. So are you asking, could I drink this now? I wouldn't, just because there might be some excess, like I might have some, unless I've got my ratio actually perfect, there's going to be leftover of one reactant or the other. And if there's leftover lead, I really don't want to be drinking lead. But presuming you could get it to go perfectly, then maybe it would be okay. Yes. Okay. And we can decant Yes, it's literally like just as easy as it could be. We can decant the liquid pour it off, and leave the solid behind. So these are just words that you should know. You should know the word decant. You should know the term precipitate. You should know the term centrifuge. You should know the term supernatant. Okay? So here's our vocab words here. I'll put little stars by all the vocab words. Centrifuge, supernatant, precipitate, decant. Those are all our, yeah, you spin it really fast, and gravity, essentially it's like the, what is it, centripetal or centrifugal force? I don't know which one it is. It's one of those forces, one of those outward forces, the spinning force. Yes. Uh-huh. How come it doesn't spill out when we're spinning it? Everything's being pushed to the side, right? Like everything's being pushed down, but the solid is more dense, so it ends up at the bottom. And anything that's less dense will end up at the top. So they'll often use something like this when they're separating out blood into the various things, like so you'll get blood cells and then the plasma. Are we gonna try, like, are we gonna take our blood and centrifuge our blood? No. We can't even, oh my gosh, you guys, you don't even know what it was like going to school in the 80s. In biology class, we got to like find our blood type. We would like to, we took a little sterile lancet. It's like this little thing, and you have to go like this to your finger, and then you milk it out, and then you put it with all the little immunoglobulin things. Yeah, and you get like a little drop, and then you put it with various like antigens, or yeah, and then you see if it clots, and that tells you your blood type. So we used to do that. We also got to dissect a pith frog, which was super cool. But so a frog that has been pithed, that's where they take the probe and scramble its brain while it's still alive. But okay, I know it sounds horrible, but what's the purpose of that? Okay, so if you pith the brain of the frog and you put it into water, its brain is completely gone, but it will still swim, because swimming is a reflex, and the nerves that go to a reflex only go through the spinal cord, not through the brain. So it's like, it really shows you, like, reflexes only go through the spinal cord, not through the brain. If you then pith the spinal cord, then you put it in the water and it does not swim. Okay? If it's brain dead and you put it in the water, it will swim. Oh, you could do that too. It won't be able to swim. Okay, so here's the thing. We probably want to scramble the brain first because that kills all the pain centers, right? So then the frog's not feeling pain. Yes? Then, oh, hold on. Then we took our pitched frog and you dissect it just like any other frog. And even though the brain is gone and the spinal cord is gone, the heart is still beating because it's on its own electrical circuit. Okay? Now, and this is why I'm like, even though it sounds so horrible, it is so cool. So it's open, the heart is still beating. Okay? Now wait, it gets better because if you cut the heart out and place it into a solution which is isotonic with blood, the heart keeps pumping. It's I'm sorry, like I know it's horrible, it's cruelty to frogs, but I was like, holy crap, this is amazing. Yes. How do we what? It's brain dead. Pain is felt in the brain. I don't know. Maybe. Sure. I'll let you guess. What's isotonic? Tonicity is to do with the ions in the water. And so isotonic means it has the same ions that are in the blood. Yes. Swing is not a reflex for you. Okay? Yes. Reflex for frogs is not a reflex for you. Although you can test it out if you want to. No, you did? Okay. Now I'm really sorry I brought this up because we need to move on with chemistry, but yes. No, you mean the heart being out and pumping? No, it should be all of them. In theory, you should be able to take like a human heart and like, oh, maybe, I don't know. You might be able to take a fish heart. You could try it. Shh. You need Ringer's solution. That's what it's called, Ringer's solution. Shh. Yes. So the reason that I had the two of them, so one of the solutions was the lead nitrate, one was the potassium iodide, and then I put them both together. Then the reason I filled up the other tube was so that they would balance in the centrifuge. Because if you have a load on one side only, the centrifuge will start to do a dance, like it does not spin nicely. Okay, so that's why we filled up the other tube. It was just water in there. Okay, yeah. Thank you for getting us back to chemistry, Daniel. I appreciate that. That was very nicely done. All right, so here we have our precipitate and our decanting and et cetera, and now we are going to go back to 6.3e, or F rather, actually. And we're going to take a look at this because did you guys understand what was going on in these diagrams? Yes? So if you have, there are three different situations you can have. This is page 70. Situation number one, no reaction. If both of the products are soluble, then there's no reaction, okay? And we know that if we have sodium as one of our ions and we have potassium as the other of our ions, neither of the products are going to be precipitates, yes? If there is no precipitate, then there is no reaction. Before the reaction, we had sodium ions floating around. Yes? After the reaction, we have sodium ions floating around. Before the reaction, we had sulfide ions floating around. After the reaction, we have sulfide ions floating around. Has anybody undergone any sort of a change here? No, we had ions floating around. Now we have a mixture of different ions floating around. This is a physical change, not a chemical change, because we've just mixed things. Yes? Because we're trying to figure out if there's a reaction or not. You know what? Once you get good at it, you can just look at it and go, oh, I got two alkali metals. No, there's not going to be a reaction. Do you know what I mean? So if you don't know your solubility rules super well, or are not able to do the switcheroo in your head, you would write out your products first, say, oh, this one's aqueous, this one's aqueous, there was no reaction. So in the end, what you would end up doing is you would say, no reaction. You would not actually write the products like that because there's no real products, there's no real reactants. There was not a reaction. Yes? There's no precipitate, therefore no reaction. Okay? Now you can have a situation like the one where we just had, where one of the substances precipitates and the other one doesn't. Okay, so we had chlorides floating around on their own in one beaker with the sodium, silvers floating around on their own with the nitrates in another beaker. When we mix them, silver says to chloride, oh my, you are too attractive, I cannot stay away from you. And they all get together and they form a what? Precipitate in the form of a, starts with a C. Crystal lattice. Okay? Now, does it always end up at the bottom? No, you can have it floating around and then it will settle to the bottom, but it's the general idea. So you can have one precipitate as a product, and then you have a reaction, of course. However, it is also possible that you have a compound that is soluble, like copper sulfate, and you mix it with another soluble compound, like strontium hydroxide, and then copper 2, when you put it with hydroxide, is low solubility, and the other product, the strontium and the sulfate, is also low solubility, so it's possible to have two precipitates in a reaction. Yes? Oh, I mean, I'm just showing the most simplified thing. Like, honestly, they all form little tiny clumps. That's why we end up with, like, just it looking cloudy. Yeah, exactly. Yeah. Yes? Yeah. You would have a hard time separating the two precipitates. So probably there would be no reason for doing this in like particular. Like, what would the purpose be? I don't know. Yeah? Yes? Probably not. Copper 2 is usually blue, so it would, you'd have some blue stuff in there, and yeah, so they would look different, but again, they would be mixed together, so you'd have one, I think this guy would be white, and this would be blue, so it would just end up looking like a lighter blue because they're all mixed in together. Yeah. Okay. Did you guys try these questions in here? These ones here? How'd they go? They went okay? All right, excellent. Then we are going to move on. We did this one, 6.38, predicting products of neutralization. Acid plus base gives salt plus water. So because, I mean, if you wanted to, you could watch Chemistry Talk with Dan, but we're going to do it together. All right, so we have sulfuric acid. So do you remember what it means when we have an ick acid? I ate something icky, yes? So that means it's the 8 ion. And are you guys thrown by the fact that there's an F in there instead of pH? I hope not, okay, because the pH is the British way of doing it, the F is the American way of doing it, and in fact, the F is the official way now, as of about 10 years ago. Officially, it should be an F, but I can't. I know it's American, but I'm just bringing this up because on the AP exam, which is based out of the College Board in the States, you will say sulfur with an F and sulfate with an F and all of those things. Yes. No, you'll be fine. Okay? Yeah. So we have sulfate, SO4, 2 minus. And who is sulfate paired up with in sulfuric acid? H. And what's the charge of H? Positive. All good, no worries. And so what would the formula of sulfuric acid be? H2SO4. And what do you know about the state if something is an acid? Has to be aqueous because otherwise it would not be acidic because it would not have those dissolved H ions. And it was completely neutralized by some aluminum hydroxide. Al, what's the formula for aluminum hydroxide? OH3. And we're going to pretend that's aqueous even though it's not. Okay? We just want to make life easy on ourselves, all right? How would you predict the products? Water and a salt, and in fact, this is just a fancy double replacement reaction, yes? So we're going to take our outside ions and put them together, and then we're going to take our inside ions and put them together. So I'm going to take my H plus is going to go with my OH minus, which makes H2O, or because it makes balancing easier, I'm going to write it as HOH. But if you're fine balancing it without doing that, you can write it as H2O, totally fine. And what state is H2O? Liquid, yeah, okay. And then we have aluminum is going to get together with sulfate. Aluminum is 3 plus, sulfate is 2 minus, so what will we have? Al, 2, SO4, 3. All right, and now we're going to balance this. And remember, you're going to balance by looking at the most complicated formula first. Who is that? Al2SO4, 3. So we're going to say we want 2 aluminums and 3 sulfates. And if we did everything well, hopefully everything else should just work out. How many hydrogens do we have? 6. And how many hydroxides do we have? 6. Guess what? How many waters do we have? 6. So you actually don't even need to, if you know that the hydroxides and the hydrogens and the waters are always equal, you don't actually have to write water as HOH. You can just write it as H2O because you know if you have 6 hydrogens, you will end up with how many waters? 6. If you have 6 hydroxides, how many waters will you end up with? 6. Okay, any neutralization, hydrogen, hydroxide, and water will all have the same number. Okay. All right, so that was beautiful. And then we have carbonic acid. So again, we have an ic acid. So who is the ion? Carbonic. Carbonate. What is the formula for carbonate? Tell your partner. CO3, 2 minus. No, but I'm going to ask you all the time so that it becomes more automatic as time goes on. Yes. I can't hear. I can't hear her. So all the rest of you need to stop talking Yes. It's not. We're just making it so we have a question that we can balance. It's hard to find ones that are interesting to balance in acids because most of the hydroxides are not soluble, right? So it's really hard to find one that has 3 hydroxides in it. Okay, carbonic acid. So knowing that carbonate is CO3 2-, what is the formula for carbonic acid? H2CO3. And it was titrated to completion. Do you care if you know what titrated is at this point? No. It was titrated to completion with sodium hydroxide, NaOH. So we are going to end up with water. And who is our other product? Na2CO3, yes. What will our states be there? Aqueous. Sodium hydroxide is got a sodium, aqueous. Water is liquid. Sodium carbonate is got sodium, aqueous. Anytime you see sodium, it must be aqueous, unless it's like sodium metal, in which case it's a solid, right? Yeah. Okay. So we have that, and now we want to balance it. So let's pick our most complicated formula. We need 2 NAs. So you'll notice we have 2 OHs, and we have 2 H's. How many waters should we have? 2. Done. Is good. And if you don't feel comfortable about that, put it as HOH, and you can balance your H's and OH's. Yes? Oh, yeah. Oh, the state, probably aluminum sulfate. I feel like that's soluble. I don't know. I'd have to look it up. I'll put AQ question mark. Okay. Okay. Let's see. We got 20 minutes left. Let's keep going. Yeah. All right. We're going to talk organic chemistry now. So this is on page 80. And what I'd like you to do is I would like you to look at the structures that you are provided and the names that are provided and try to fill in the blanks in the table. Okay, so this is page 80. Eight zero. Use your pattern matching ability to fill in those blanks. 8-0. little hint. When you get tired of drawing H's, if you just draw sticks, everyone will assume there's H's on the end. So a stick with nothing on the end has an H on the end. But if it's coming off of an oxygen, make sure you put the H. Okay, it's just if it's coming off the carbons, you can just use stick. Save yourself some effort. You committed to H. I hear you. Yep. And once you're done page 80, you can start working on page 81 and 82.
If I don't understand something, then I'll stay here. Because technically I didn't sign up for this meeting. Well, no, because Brendan and David, I think now do like club running, so they're just wrecking me all for the morning.
Yeah, so if you're allergic to peanut butter, you can eat peanut bread instead. Hi. Yes. No, this isn't linear either. Often when we draw the structures, we don't draw them in their real form. I mean, quite frankly, this is the angle is they're really yes, and when you get into doing lots of organic drawing, so you'll just be like this. right? Yeah. So you're like, oh, I know that
It's depressing. So I do that, and then I was busy shaving there. I'm like, you know what? This is just like literally what I heard. And then he's like, yes.